Hi, I'm Ryan Baker, and welcome to Big Day in Education. Welcome to the 5th week of the class. You're half done. Today we're going to talk about relationship mining, and in specific, correlation mining. Relationship mining is where you try to discover relationships between variables in a data set with a whole lot of variables. And there's a lot of types of relationship mining. It's actually a really big and broad area. The first and the one we'll talk about today is correlation mining. In correlation mining, which is probably the simplest form of relationship mining, and it precedes people thinking about data mining by decades, you just try to find substantial linear correlations between variables. And you may remember linear correlations from earlier in the class, week 2, in a large set of variables. Some of the use cases that you might think about include you have 100 variables and you want to know how each one correlates to a variable of interest. Now this is not quite the same as building a prediction model. A prediction model would try to find the best combination of those 100 variables to predict that variable of interest, whereas in this case, you just want to know how each one individually correlates, and you don't care about getting the single best model across variables. In other cases, you have 100 variables, and you want to know how they correlate to each other. You want to just have a gigantic matrix. Now, of course, 100 variables might not be all you have. You might have 10,000 variables, or 1 million variables. Although, if you have 1 million variables and you look at each of them individually, you might not want to look at the correlations for all the million. You might want to look at only the best, say, 100. There's a lot of uses for this in education. One of them is studying relationships between questionnaires on traditional motivational constructs, like goal orientation, grit, and interest, and student reasons for taking a MOOC. I wonder if anyone's doing research on this problem. Oh well. Second one is correlating the features of the design of mathematics problems to a range of outcome measures. And actually, my research group has done some work in this area. The third one might be correlating features of schools to a range of outcome measures. What are the aspects of the good schools? Now you might think, hey, let's just run 100 correlations and we're done. Well, that's kind of what you do, but there are some challenges. First of all, let's say you run 100 correlations or 10,000 correlations, and 9 of them come up statistically significant. Which ones can you trust? Which of these correlations, is it just that you take these 9 and you say, we're good, these 9 effects are real? Well, if you set p equals 0.05, then just assuming random noise, 5% of your correlations are going to turn up statistically significant, which might be a problem if you're doing 10 million correlations. The problem comes from the paradigm of conducting a single statistical significance test, and it's kind of why data mining is largely a different paradigm than statistics. But the solution is well known, and that's to adjust for the probability that your results are due to chance using what's called a post hoc control. There are 2 paradigms for post hoc controls. The first one is FWER, family-wise error rate, which controls for the probability that any of your tests are falsely claimed to be significant. So in this case, you want to say, how can we guarantee that nothing we let through is actually junk? The other one is FDR, false discovery rate, where you try to control for the overall rate of false discoveries. You say, I'm actually comfortable with 5% of my results being junk. I just don't want more than 5%. The classic approach to FWER correction is the Bonferroni correction, and there you can see Bonferroni down there at the bottom corner, which ironically was derived by Miller rather than Bonferroni. Now, ironically, there also appear to be no pictures of Miller on the internet. See what happens when your discoveries get named after somebody else? To digress just a little bit, this is a classic example of Stigler's law of eponymy, which says that no scientific discovery is named after its original discoverer, which, ironically, was proposed by Robert Merton. Anyways, if you're conducting n statistical significance tests on the same data set, then under a Bonferroni correction, you adjust your significance criterion alpha to be alpha divided by n. So you take the significance criterion alpha, usually 0.05, and you divide it by the n, the number of tests you did. In other words, for 4 statistical tests, you take 0.05 divided by 4 and use the statistical significance criterion of 0.0125 rather than 0.05. Let's give an example. Let's say you run 5 tests and you get p of 0.04, p of 0.12, p of 0.18, p of 0.33, and p of 0.55. In that case, you do 5 corrections. All p are compared to alpha's 0.01, nothing significant anymore, and the p of 0.04 is seen as just being chance. Is this okay? I don't know. I'm okay with it. Seems kind of reasonable to me. Let's say, by contrast, that we have 5 tests of p of 0.001, p of 0.011, p of 0.02, p of 0.03, and p of 0.04. We got 5 tests, and they're all statistically significant. We do 5 corrections, we compare all the p to 0.01, and we say that only the p of 0.001 is still significant. We've got 5 out of 5 cases were statistically significant. Think of what the probability of that is. You've got 0.05 to the 5th power that you're going to get 5 statistically significant results out of 5, and yet Bonferroni is throwing 4 of those 5 out. Is that right? I'm not sure. Now let's talk about the Bonferroni correction. There are some advantages. First of all, you can be certain, so to speak, that an effect is real if it makes it through the correction. And it doesn't assume that tests are independent, which is good. Some variants on Bonferroni that are a little less conservative, still within the FWER paradigm, think that you have to have independent tests. The main disadvantage is it's massively over-conservative. If you do a lot of correlations, it's going to throw everything out, and a lot of genuine effects will just go into the wastepan.
So, despite its continuing popularity, Bonferroni has been criticized for many years. It's just, I think, an out-of-date correction.
There are FWER corrections that are a little less conservative than Bonferroni. People have been worrying about this problem for a while, including Holmes correction or Holmes step down. Sounds pretty awesome, right? Like a dance. Tukey's honestly significant difference. That's a name. How can you argue with an honestly significant difference? The Sidak correction, I like that one relatively. But these are all still generally very conservative because they still all try to make sure that none of your tests are going to be not statistically significant. They want to make sure everything's okay. And this leads to discarding results that probably shouldn't be discarded. By contrast, there's the FDR correction, which was proposed by Benjamin and Hochberg. We see there a picture of FDR. It's a different paradigm, arguably a better match to the original conception of statistical significance. Because the original conception of statistical significance is you want p of less than 0.05, which means that you treat a test as rejecting the null hypothesis if there's a probability of under 5% that the result could have occurred if there was only random events going on. So in other words, if there's just junk, what's the probability you'd see the result you saw? And this paradigm accepts from the beginning that we're going to accept junk, also called type 1 error, 5% of the time. By contrast, the FWER correction says that each test is treated as rejecting the null hypothesis if there's a probability of under 5% divided by n that the results could have occurred if there were only random events going on. And this paradigm accepts junk far less than 5% of the time. Finally, there's the FDR correction. Again, p is less than 0.05, and across tests we say we're going to attempt to accept junk exactly 5% of the time. And this is the same degree of conservatism as the original conception of statistical significance. So in other words, if you use Bonferroni, you're actually saying, I want to be far stricter than Student or the Fisher or the original developers of statistical significance. FDR says, I want to be just as conservative as Student. So let's talk about Benjamini and Hochberg's FDR procedure. And there are others, and I'll talk about a couple in a minute. In the FDR procedure by Benjamini and Hochberg, you order your n tests from the most significant, the lowest p, to the least significant, highest p. Then you test your first test according to the significance criterion alpha times 1 divided by n. So on the first test, you're going to be just as strict as Bonferroni. On the second test, though, you're only going to be half as strict as Bonferroni because you'll test your second test according to the significance criterion alpha times 2 divided by n. And the third test, alpha times 3 divided by n, and the kth test by alpha times k divided by n. And you're going to quit as soon as the test isn't significant. As soon as the test is not significant, you just move on. So let's take the example that we looked at earlier with Bonferroni. And you may remember that with Bonferroni, we're going to throw out 4 of these 5. With FDR, we're going to look at them. We got 0.001. Well, we compare 0.01 to alpha of 0.1. Still significant. Same result as Bonferroni. With the second one, 0.11, now we're going to compare it to 0.02. Still significant. Third one, 0.2 compared to 0.03. Still significant. Fourth correction, we're going to compare p of 0.03 compared to alpha of 0.04. Still significant. On the fifth correction, we're going to compare p of 0.04 compared to alpha of 0.05. And this is still significant. So in other words, with the FDR correction, we're going to say these 5 tests, each of which was statistically significant to begin with, are still statistically significant even after we do the FDR correction. And that's probably right, because again, the odds of getting 5 statistically significant results out of 5 is 0.05 to the 5th power. Pretty unlikely. How about the 0.04, 0.12, 0.18, 0.33, 0.55, where Bonferroni threw everything out? Well, we do the first correction, p of 0.04 compared to alpha of 0.01. It's not significant, we stop. So actually, for this case, where we probably do want to throw everything out, FDR is just as strict as Bonferroni. So conservatism. FDR, Benjamini Hochberg, is much less conservative than the Bonferroni correction, but it's much more conservative than just accepting P of 0.05 no matter how many tests are on. I think it kind of hits a sweet spot. You may disagree, but the point is if you're using something like Bonferroni, you're being really, really conservative.
Now, in talking about Benjamini and Hochberg, it's important to note a, honestly, fairly uncommon special case that you still might come across. If your stat tests have negative regression dependency, in other words, if one of your tests being significant makes it less likely that other tests are significant, then you can't use Benjamini and Hochberg, and you have to use another more complex control, Benjamini and Yacoutieli. And this shows up, for example, when you're studying the relationships between one variable and a group of variables that are mutually exclusive with each other. So it's kind of a special case, but for example, in affect dynamics work it shows up. And I want to give a hat tip to Shamya Karambaye and Jeff Matayoshi on this one. They published a great paper that kind of pointed out this issue, and it pointed out that a lot of people were making this mistake, including me.
I want to briefly talk about one other post hoc method, and that's the Q-value extension in FDR by Story. Recall that P, in traditional statistical significance testing, is the probability that the results could have occurred if there were only random events going on. In Story's test, we transform P to Q. Q is the probability that the current test is a false discovery, given the post hoc adjustment. One funny thing, Q can actually be lower than P, in the relatively unusual case where there are many statistically significant results. So if you have 5 out of 5 statistically significant, then Story's test says, well, gee, across the whole pattern, it looks pretty significant, so let's trust these values a little more. So you can, in rare cases, actually have Story's correction take something that would have been marginally significant with no adjustment, say P of 0.06, and it becomes a P of 0.045. It's rare, though. I've only seen this happen once. Incidentally, for those of you who are R lovers out there, the only package that really can do Story's adjustment right now is in R. So if you've been spending the whole class going, why are they using RapidMiner? We should be using R. I love R. Well, here's your chance. This is an R. So, a closing thought. Correlation mining can be a powerful way to see what factors are mathematically associated with each other. But it's important to get the right level of conservatism. If you're too conservative, you throw out everything. If you're not conservative enough, you accept junk. And you may be saying at this point, it's great that we have all these correlations, but we all know correlation isn't causation. Well, I agree with you. And in the next lecture, we're going to talk about a method called causal mining that under the right usage can allow you to move from saying these two variables are correlated to saying there's a causal relationship. So, I'm Ryan Baker. This is Big Day in Education. See you next time.